Good afternoon. My name is Jean-Louis Briot. I'm the Spencer J. Buchanan Professor in the Department of Civil Engineering at Texas A&M University. I wish to welcome you to the 7th Buchanan Lecture. In a short while, I will invite Dr. Roland Hayden to say a few words of introduction. Before that, let me go over the program. After Dr. Hayden's remark, Professor Don Murph will introduce Professor Mike O'Neill, who will follow with the delivery of his 1998 Tersaghi lecture on the topic of site resistance in deep foundations. We'll take time for questions, and then I will have the pleasure to introduce Professor Mike Duncan before he delivers his Buchanan lecture on the topic of factors of safety and reliability in geotechnical engineering. A question period will follow and will be led by Mr. Darrell Hooper. Finally, Dr. Philip Buchanan will thank the Buchanan lecturer. Now let me introduce Dr. Hayden. Dr. Roland Hayden is the Vice Chancellor for Engineering of the Texas A&M University System. He's also the Dean of the College of Engineering at Texas A&M University at College Station and the Director of the Texas Engineering Experiment Station. I've asked him to give us a short summary on the state of the College of Engineering at Texas A&M University.
Thank you, Professor Briot. It's a real pleasure for me to be here with you today and to see what a great assemblage we have, a very nice crowd for this distinguished lecture series, one that now has become one of almost long-standing with this many years on it. And the one thing I've learned since coming back to A&M after almost a 20-year absence, I was on the faculty before, is that if you have something twice at A&M, it becomes a tradition, and that means you have to have it forever then, because we're very closely bound to tradition at Texas A&M, as you all know. I see by the smiles on faces out in the audience, and we certainly intend to do that. It's a real honor and privilege to have these two distinguished professors in this lecture series this afternoon and affiliated and tied and present on our campus. You do us great honor by your presence, and I want to say thank you to both Professors Duncan and O'Neill for being willing to do this. They're our colleagues at sister institutions, one not so far away from us and another quite some distance away from us, but in many ways like us at Virginia Tech, being a land-grant institution. So again, I want to say thank you to both of these gentlemen for being with us today. I also want to tell you that we're honored by the presence of one of our Board of Regents, Dr. Don Aviles, and if I would ask him maybe just to stand over here. Most of you know Don, I think, or many of you do. He's a member of our profession, and it's a real honor to be able to get one of our Board of Regents to one of these meetings. So I'm just delighted Don could be here, and he's not only one of our civil engineers, but he's also a very close friend of our engineering program. Well, as Jean-Louis promised you, I want to give you just a few facts, but I won't make it so long as to bore you totally to death. Keep it fairly brief. But let me say to you that the college and the program in engineering is in good shape. We think it's hopefully in good hands as well. I think with people like Jean-Louis, we could certainly say that for the faculty. But things have continued to grow and progress, sometimes maybe faster than we would like. We are now at an enrollment level in our college of just under 10,000 students. So we're at 9,900 almost exactly. And last year was the largest entering freshman class ever into engineering at Texas A&M University. We had almost 2,200 freshmen. And frankly, that was just a little bit more than we had anticipated. Our target is to have about 1,600 And you might say, well, gosh, maybe you guys aren't such good engineers. You do do a better job modeling this situation, right? Well, it was a little bit beyond our control in that there were some entrance things the state put on us and this, that, and another that made it very difficult to estimate since we don't have an absolute cutoff. So we do have to model it, in fact. This year we were a little bit more fortunate in the sense that we had 1,750, so we still overshot our target of 1,600 freshmen. But we're getting a little better at our model. You can see we're only 150 over instead of 500 or 600 over. The faculty, of course, has responded very well to this. We know it's extra load, but they have taken on that burden, and we think we're providing quality education in our engineering programs, and certainly that applies to civil engineering and things related to soil mechanics and the kind of things that you all here are interested in so much today. Our research area continues to be very healthy. This last year we ranked 5th among research colleges of engineering. So the year before we were 4th, but we got jumped over by Michigan. This year we kind of vary back and forth. We've been as high even as 3rd 2 or 3 years ago. It just depends on what we do in a given year and what the other schools do. But last year in our research programs that are tied to faculty, and that's the way they count them, we expended $105 million in engineering research. Now, actually, overall in research, we expended more than that because a lot of our effort in the program, as you know, is tied to the experiment station and to the Texas Transportation Institute, and a fair amount of research is done by staff engineers. And we say, well, it's not necessarily exactly tied to faculty, so we don't count it the same way. But still, this places us, in terms of research effort, right along with people like MIT, Michigan, Georgia Tech, and I forget who the other one was now. But I guess I could say to you we are right up there near the top in terms of dollar expenditures on research. Our ranking this last year by U.S. News was 14th among graduate research programs. Actually, our civil engineering program is ranked higher than our college overall. Because we ranked 10th at the undergraduate level and 11th at the graduate level. So you can see we continue to have, as we traditionally have had at Texas A&M, a very, very high quality, high caliber civil engineering program. And that, of course, is due to our outstanding faculty, number one, and our outstanding students, number two. And our dean is somewhere way down the list, right, John? But it certainly makes me, the dean, very proud to see our civil engineering department doing so well and being thought of so well by our peers and by people in the industry, because they also have a say in that. The university overall also, I think, is in good shape. We had a pretty good legislative year this last session. Our faculty got raises, which was nice. We got some additional money here and there for programs as well. Not a lot, so it was a moderate year, but certainly good in the sense there were raises. The university overall continued to grow a little bit. We haven't really been trying hard to do that, but this year we are at a little over 44,000 students at Texas A&M. So this would place us probably 4th in size amongst campuses in the United States. So again, there's a lot of young people, most of them, some old people actually, amongst our students too, but mostly young people that have come to us, placed their confidence in us, their trust in us, their trust in our former students as well, who've been so supportive in terms of scholarship dollars, in terms of jobs. You all provide those positions that they need when they finish. And we hope we're up to the test. We think we're up to the test. And we pledge our best efforts to you in making good things happen for these students. Again, we're just delighted that all of you have seen fit to attend the lecture series today, and we welcome you to our campus. If you're new to our campus, if you're returning, we still welcome you. Thank you.
Dr. Murph received his PhD from Texas A&M University in 1972. Many of you know him. He worked for many years for Exxon Production Research, where he developed an international reputation as a wise and soft-spoken engineer dealing with geotechnical engineering for offshore platforms. He retired from EPR earlier this year and joined our group shortly after that.
Well, thank you, Jean-Louis. I've been looking forward for a long time to my retirement and slowing down the pace a little bit and having the quiet, contemplative life of a university professor. And so far, I'm still looking forward to that at some point. I found this that I'm scrambling just to stay ahead of my students these days. But it's been a lot of fun, and I'm very happy to be here. It's a great pleasure for me to introduce our first speaker today, Professor Michael W. O'Neill, who's the Cullen Distinguished Professor at the University of Houston. Over the past 30-some-odd years, Mike O'Neill has distinguished himself teaching, research, engineering practice, and professional service. He has conducted a wide range of research projects, has served in a leadership capacity on academic, professional, and government committees, and has published over 150 papers and reports in his area. Most of his activities have been focused on the subject of deep foundations, especially piles, driven piles, and drill shafts. He has been honored by his peers on many occasions, receiving awards such as the Walter Huber Research Award from ASCE, and more recently the 1998 ASCE Carl Terzaghi Lectureship. It is noteworthy that he has also received the Service to the Profession Award from the Association of Drill Shaft Contractors. I might add that this is not a group known for their tolerance of blue sky research. I think this is an important point, for when I think of Mike's work, the word relevance comes to mind. He seems to be driven by providing something useful. On a personal note, I first met Mike in 1972 when I first started to work for Exxon. We were going to build a demonstration drilling structure in Friendswood, and Mike carried out the site investigation for the cellar deck, or for the cellar for that particular job. I remember that I was impressed then that even though this was a small job, Mike was extremely diligent, and he was very interested in how his results would be applied and making sure that we understood what he had done in providing us with sound guidance. I've been very fortunate to cross paths with Mike many times since then, and his approach and attitude have never wavered. I'm very honored to introduce Mike O'Neill presenting the 1998 Terzaghi Lecture, Side Resistance and Deep Foundation.
Thank you a lot, Don. You know, after the honor of being asked to give the Terzaghi Lecture sunk in, I began to think about what I should be talking about. And considering that I'm a deep foundations person, I wondered about the appropriateness of someone with my background giving a lecture to honor Carl Terzaghi. After all, Terzaghi wasn't exactly consumed by an interest in piles. But I decided to speak on side resistance in deep foundations anyway, because that's a subject that's always intrigued me. Terzaghi admitted he didn't know much about skin friction, as he termed it. He developed a few graphs based on earth pressure theory, but he apparently didn't have much confidence that there were practical use. Instead, he admonished his peers and students to perform site-specific load tests to measure skin friction, which of course remains good advice for us today. Years later, Alex Vesic expressed his appreciation of the difficulty of attacking the problem of pile resistance analytically somewhat differently. Building on earlier work, Vesic conceived and promoted the concept of the that the stresses or the stress field in the vicinity of a pile could be estimated by invoking a relatively simple theoretical model in which we envision the soil to act as if it were being thrust outwards by an expanding cylindrical cavity. While the version of that theory advanced by Vesic didn't lead directly to practical solutions, it did provide a framework for understanding some of the soil properties that have a strong influence on skin friction, and will from time to time refer to that theory. An entirely different way, of course, of dealing with the problem might be to emulate our colleagues in other cultures by appealing to the piling deities before we begin construction. Sometimes when we deal with piling, this offers the best opportunity for success, but today we'll leave this approach to those who have employed it and practiced it and go on to some other solutions. Coming to the present, I was privileged a few years ago to introduce Roy Olson as a Terzaghi lecturer. Roy is in the audience. I hope he doesn't mind me speaking of him, but he's an engineer who's had considerable influence on the development of methods for the design of axially loaded piles. And when I asked him about the topic of his lecture, he told me he would speak on consolidation, for which, of course, he's also very well known and respected. Roy told me he'd had considerable thought about talking about piles, but he'd finally decided he just didn't want to open up what he called that can of worms. Well, considering the old fools and angels line, I decided that since Roy passed on the opportunity, it might be interesting at least to try to peek into the can of worms. So here we go. Now, first of all, the problem of getting a comprehensive handle on side resistance, the term I'll use instead of skin friction, involves just too many topics to cover today. I think it's appropriate right off the bat to declare what we're not going to cover. And these are the topics we're not going to cover. Not that these issues are not important, but I'll leave them to other times. At least when I planned to give the Terzaghi lecture, these were all the topics I thought I would cover. Considering the fact that my original version of the Terzaghi lecture ran about an hour and 25 minutes, I'll spare you some of these and we'll catch the main ones. First, we're going to take a look at this topic of side resistance, looking at this little red box in the bottom, which I think is rather important. And for you students, I think this is a good indication of how research is done, how engineering is done. We learn about engineering not from developing some grandiose mathematical model and then going out and verifying it in the field and then finally using some design inferences from that model, but rather we observe things. We try to use inductive reasoning to find out what are the underlying principles. So we go from what we observe to the underlying principles. We develop some sort of model. I call that theory. And from that, we come back down using deduction to develop design inferences. So induction, deduction is the way we normally think. Now, a lot of academics may not agree with this. Perhaps my opinions in this matter will provoke debates and spitting contests, but I think this is one of the purposes of a Terzaghi lecture. In our profession, the purpose of theory is to expand and generalize our observations and finally to help us produce guidelines for design, and I want to follow that theme throughout. Let's think of this as the problem definition slide. I view the problem of estimating side resistance from a traditional perspective. The surface of failure is at or near the surface of the pile, and the shear strength of the soil is controlled by the normal effective stresses along that surface at the time we load the pile. Sigma prime sub h in this particular figure. That stress there. The rub, of course, comes in evaluating these effective stresses, which can perhaps be estimated from the ambient vertical effective stresses, sigma prime V naught, that stress there, and the earth pressure coefficients, which I term either K sub I or K sub C, and, of course, the shear strength parameters of the soil. As I'll discuss these various issues, I'll refer to K sub I and K sub C, respectively, the earth pressure coefficients related to the conditions immediately after installation and to the conditions after all pore water pressures have stabilized or after consolidation. Knowing these parameters, we can proceed to compute the peak unit side shearing resistance, which I term F max. as a function of depth, and then we integrate that resistance over the surface of the pile to evaluate the total side resistance, the resisting force R sub S. There's some complicating factors about this that make this not quite so simple, especially those related perhaps to progressive failure that we'll look at later. One of the issues that's been motivated by offshore development in the last 25 years or so is that of making static estimates of the resistance of very long driven piles in cohesive soils. To be sure, our static estimates can be improved by performing stress wave analyses on piles as they're driven, but pile links need to be ordered, and construction operations have to be planned before such measurements can be made. So despite recent high-tech advances, stress wave analysis primarily, we still can't get around making estimates of R sub S from soil properties and good engineering judgment, perhaps. Let's consider what Meyerhoff had to say on the subject in his 1975 Terzaghi lecture, which was published in '76. He described the underlying phenomena and then suggested the alpha and beta design methods for driven piles in saturated clay. In the alpha method, which of course is a total stress method, the changes in effective stress and soil structure brought about by the driving of the pile and the effective stress path of the soil along the pile that it undergoes during installation and loading are all collapsed into one factor called alpha, which in both derivation and application is empirical. The alpha method has been derided as inadequate because the undrained shear strength of the soil, which I term S sub U, is not really a unique soil property. It's rather just an artifact of the way the soil is tested. And because the problem is really an effective stress problem, not a total stress problem, nonetheless, the alpha method is practical and continues to be used. We'll say a little more about it later. On the bottom half of the slide, Meyerhoff also described the beta method. This method satisfies our need to analyze the problem as an effective stress problem. We simply multiply the vertical effective stress at some level by the product of an earth pressure coefficient, which is proportional perhaps to K naught, at least in Meyerhoff's procedure, times the inclination of the effective resultant against the pile wall, which Meyerhoff took to be the tangent of phi prime. Of course, the critic would ask, which phi prime? At this point, but we'll understand it to be the value corresponding to the maximum principal stress difference in drain triaxial compression testing. K naught for cohesive soil was 1 minus the sine of phi prime times the over-consolidation ratio raised to the power 0.5, which was a curve-fitting expression for experimental data on the effect of over-consolidation ratio on K naught. He also stated that from field test, he observed that F max was higher than sigma prime V naught, K naught, tan phi prime, the basic friction formula, by a factor of 1 to 2 in over-consolidated London clay, which he was focusing on at the time. So I've inserted the empirical multiplier of 1.5 here. I don't believe that Meyerhoff was ever that specific, and it'll have some influence on some comparisons I make a little bit later. So that 1.5 is my factor and not his. But as the story unfolds, we can get a sense that the predictability of F max in over-consolidated clays may be a bit more uncertain than in normally consolidated clays. Looking into the issue in a little bit more detail, we envision that the driving of a displacement pile into saturated clay produces a zone of highly remolded soil around the pile. Within that zone, elevated pore pressures exist with a high hydraulic gradient, shown here in the red line, which is a little bit difficult to see. Those excess pore pressures, of course, dissipate, which obviously changes the effective stresses of the soil in the disturbed zone. But the volume change resulting from the exiting pore water also results in a change in total stress against the pile wall, making the tracking of effective stresses from driving to loading more difficult. You've got both the total stress and the pore water pressure changing. The elastically stressed soil in the blue outside the disturbed or plastic zone acts to restrain the plastic soil with perhaps something like a constant lateral stiffness. At least that's one view of the problem. Again, we'll assume for now that F max is proportional to the normal effective stress at the interface at the time the pile fails under axial loading. We're automatically assuming that the driving process destroys any cohesion that might exist, so the problem is completely frictional. Now, pursuing my observation before theory theme, some years ago we measured earth pressure coefficients in the ground at rest and against 5 heavily instrumented driven piles, and they were all closed-toe pipe piles, I might add. The site, which was in Houston, consisted of saturated clays of varying plasticity and had been over-consolidated by desiccation. Consider this slide. These are our average measurements of earth pressure coefficients versus depth. The red line on the left is K0. We can see that K sub I over here is clearly 2 to 3 times K0 near the middle of the pile. That's after the pile has been driven. And K sub C is a little bit higher than K sub I. I put K sub I in quotes here because by the time we could read the total and pore pressure cells, a good bit of pore pressure dissipation had already taken place, so that's really not the true value. As I say, K sub C was slightly larger than K sub I throughout most of the pile, indicating that the consolidation process resulted in an increase in effective stresses against the pile, which would, of course, imply time-dependent setup, which we were, in fact, able to measure. Remember, this is a rather heavily over-consolidated, very stiff clay. Well, with that sort of observational information, one is tempted to proceed directly from K sub C to F max. For example, we can assume that there are no changes in pore pressures against the piles in the over-consolidated clay during slow monotonic loading, and that the highly disturbed clay is in a residual strength state, no cohesion. These assumptions let us invoke the equation in the little blue box up here to calculate F max. If we measure K sub C, we use the residual effective angle of internal friction. Of course, sigma prime V naught is a rather easy quantity to measure. We can make a prediction of skin friction versus depth, and that's what's shown here in the dashed line. In fact, we're mildly successful in reproducing the measured values, which are shown in red, by doing this, but of course not completely, as we can see. This exercise, however, demonstrates the importance of the parameter K sub C. If we look at the stress paths that were measured during compression loading of these piles, we see that our assumption regarding changes in effective stresses are not quite valid. In the upper part of the piles, where the clay is plastic, which is denoted by the solid or unbroken lines, pore water pressure increased during shear loading and effective stresses became smaller, possibly explaining in part the over-prediction of F max by the simple equation on the previous slide. Near the bottoms of the piles, where the clay was less plastic, rather sandy, denoted by the dashed lines, pore pressures and effective stresses were about as assumed. Very little change during loading. Well, we seem to be getting a handle on the problem, right? Well, if we expand our view a little bit, things look somewhat different. A consortium of oil companies sponsored a major load testing program for deep penetration piles in the UK a few years ago. A pile 0.76 meters in diameter and driven open-ended but plugged to a depth of about 59 meters was tested at an over-consolidated clay site called Tilbrook Grange near Cambridge. Our test on much shallower piles in Houston in a formation known as the Beaumont Clay exhibited normalized stress paths that seemed to converge to a straight line along the point of slippage. These arrows indicating the Houston tests here. These two solid lines are the stress paths. But no such proportionality existed at the measured slip points for the Tilbrook test, here and here. Almost a reverse proportionality. There may have been a considerable true cohesion component of shear strength in the upper till for some unexplained reason. We don't know. The point is that, in fact, the angle of wall friction between the soil and the pile may have been vastly different between the upper and lower parts of this formation, which is a theory that some people have advanced. But the point is that these two sets of tests in over-consolidated clay don't really show any discernible pattern in their normalized stress paths, suggesting that our simple K sub C sigma prime V tan phi model may not be too useful after all, and suggesting at the same time that the beta method, which works with effective stresses, carries with it considerable uncertainty in this type of soil. And if you haven't noticed by now, I think I'm beginning to set up Professor Duncan's lecture. Or perhaps the measurements at one or both sites were faulty. There's no evidence that this happened, but these measurements are difficult to make when you start to try to make measurements, particularly of total stresses against piles, are effective stresses. And any analyst, you people who work with finite element models and so forth, should be very cautious when assuming that the measured stresses are any other kind of, against piles or any other kinds of measured stresses or displacements in soil masses are the ones that you absolutely should be testing your analytical model against, because experimental measurements can be in error as much as your analytical model. Well, to put things in perspective, we measured values of beta versus depth for long full-size steel pipe piles at 3 normally consolidated and 2 over-consolidated clay sites. Beta appears to be nearly constant on the left for soils that are nearly normally consolidated at a value of about 0.7 or 1.7. In over-consolidated clay, over here, however, they're all over the place. And this is for the Houston site and the Tilbrook Grange site, the two that we've just talked about. Beta just doesn't appear to be a predictable function of either depth or over-consolidation ratio. So at this point, our observations sort of fail us, and it's time to turn to modeling. The first efforts at purely analytical solutions for this problem in clay, and particularly saturated clay, were sponsored by the oil industry to predict side resistance of very long piles, for which very little empirical data existed in the 1970s. The first research that I'll talk about was performed under the technical direction of Melvin Essrig, and it established a modeling process that required knowledge of the in situ stress state in the soil as well as several soil properties. Modeling then, and we'll let the image on the left here represent that. This is the in situ stress state, this is a profile view, and this is a plan view. Modeling then progressed to the effect of cylindrical pile installation on the effective pressures in the soil using the expanding cavity theory, and we'll let this image represent that. The effective stresses after consolidation. Of course, we have a disturbed soil here that has to consolidate. The stresses change, usually reduce, and we'll let this image represent that. And then most subsequent analytical models, by the way, have gone through the same sort of process, although the particular procedure for modeling these effects are considerably different. Finally, we have the effect of loading over here in the fourth slide. This model was known widely at that time as the General Effective Stress Model, or the GESM. Installation was modeled by the undrained expanding plane strain cavity method. The mean effective stress in the plastic zone was equated to the mean effective stress at the critical state at the void ratio encountered in the free field, which was then reduced empirically. It had to be, because it didn't work otherwise, by a factor of 0.6 to account for the extreme remolding that occurs in the driving of displacement piles. So we do have an empirical insertion into this otherwise completely analytical model. The mean total stress came directly from elastic plastic von Mises procedures that are depicted here, and that mean stress was dependent upon the Young's modulus and the undrained shear strength of the soil. Of course, could have had uncertainties about what value of S sub U should be used, undrained shear strength, and what value of E sub U should be used. There are obviously many possibilities, and so the method in terms of translating practical information to predictions of capacity has some uncertainty in it. Radial consolidation was then modeled by considering the framework of the soil in the plastic zone to be elastic, compressible, and isotropic. The modulus of the soil varied in a radially nonlinear manner from a small magnitude at the pile surface to its undisturbed value at the outer edge of the plastic zone. With this assumption, the increase in mean effective stress at the pile-soil interface during consolidation was about a third of the initial excess pore water pressure that was generated due to pile installation. The soil is at or relatively near the critical state line after consolidation, according to this model. So it was assumed that at the interface, the mean effective stress at failure is equal to the mean effective stress after consolidation. Test in Houston showed that's probably not quite true. I'm personally more familiar with what we call the VCONS axiplane model, which was developed by a student of mine, Heidinger. Similar, very similar to the GESM, but it has a different way of including the empiricism. It empirically considers the soil in the plastic zone to have anisotropic stiffness rather than isotropic stiffness, with a ratio of tangential modulus to radial modulus of about 2. Otherwise, the numerical solution of Leifer, which was used in the GESM, was also used to compute the effective stresses at the end of consolidation in this particular model. And what we see here are the conditions after pile installation, which represent the initial conditions for the consolidation modeling. If we used a constant isotropic Young's modulus in the yellow zone, the disturbed zone, we slide directly back into Terzaghi's one-dimensional consolidation theory and are forced to conclude that the change in effective normal stress on the face of the pile during consolidation is equal to the initial excess pore water pressure. Observations tell us this doesn't happen, that the effective stress changes are usually not that large, so as a minimum, it's necessary to use a model such as the GESM or VCONS with radially varying moduli to reproduce at least approximately what we observe. This is a typical result from VCONS for the Houston overconsolidated clay site, which I talked about earlier. For reference, the ambient effective stresses are indicated along the right axis. These are here, the vertical stress and the horizontal stress. The horizontal stress at this site being slightly greater than the vertical stress at the depth at which we're doing the modeling. We predict significant increases in all three major principal effective stresses near the interface. The biggest increase between driving and end of consolidation occurred in the tangential effective stress direction because more volume change occurs near the interface where the greatest pore water pressure dissipation takes place, leading to arching of stresses in the tangential direction, particularly if you make that direction stiffer than the radial direction. With this model, the radial effective stresses against the pile wall are about 2.4 times the ambient horizontal effective stress in the ground, which is consistent with the observations that I talked about earlier, which we made on the test piles. After determining these relations, Heidinger computed Fmax with a finite element code. The predictive results for VCONS for driven displacement piles and saturated clays with various stress histories are summarized here. The model appears to be reasonable over a fairly wide spectrum of soils, but again, it contains empiricisms. A significant advance came with the coupling of Balig's strain path method and the MIT E3 constitutive model in the late 1980s by Whittle. The strain path method offers a better solution for strain changes in soil around a pile as it penetrates by using the theory of the analogy of a viscous irrotational fluid flowing past a blunt fixed object. It's very different from the cylindrical cavity theory that we've used in the previous models, the cylindrical cavity that just magically expands. We realize that's not what happens when we install a pile. The E3 constitutive model tracks those strains by assuming that the soil is completely nonlinear. Irrecoverable strains are generated when stresses are reversed, which happens in many soils. It then tracks the stress-strain behavior of the soil framework as it consolidates around the pile during loading in a finite element environment, pretty much like the other methods, except that it uses a different constitutive model. There's no need in this model to assume any anisotropy in Young's moduli or any variations in Young's moduli with radial distance, as was done in the previous models. This model predicts beta of about 0.10 for normally consolidated Boston blue clay and about 0.21 for lightly over-consolidated Boston blue clay, which pretty well bracket the values of 0.17 that I showed on the slide before. In fact, on the slide before, the values vary from about 0.1 to 0.21. And so if we agree that some of the soils in those tests were slightly over-consolidated and not truly normally consolidated, then they're behaving much like the Boston blue clay would be predicted to behave using this model. It's in this model, by the way, or in the beta method. If we apply this model to calculate beta for the beta method, it's extremely important that we know what K naught is. We need to be able to compute beta with a confident value of K naught. This model shows what happens when we try to put it into practice. shows, first of all, that the radial consolidation of soil with a vertical shear stress, a residual stress against the pile, will produce a higher value of F max without a vertical shear stress, provided the subsequent loading doesn't reverse the direction of shear stress. Whittle analyzed, among other things, a series of uplift tests, which I've tried to summarize here, performed at the NGI Haga test facility in highly overconsolidated crustal soil. Our bad actor. I think this is a perfectly horrible test facility, I'll say. I hope there's nobody from NGI here, because just below the crust is a normally consolidated clay. It's not a very good place to test your theory, and in fact, the theory didn't work all that well, because we have one point here that's down near the bottom of the pile, which is way off the predicted curve. The discrepancy at that point, which was the lower measuring point, was speculated to be the result of the layering and the boundary effects emanating from the toe, where you had an over-consolidated clay overlying a normally consolidated clay. But here, nonetheless, are the range and measurements of F max along the middle of the pile among the 16 identical piles that were tested. And we compare the measurements and the predictions. The predictions by the MIT E3 model are completely theoretical. There's no empiricism built in, and we can see that it does a fairly good job of predicting what was measured if we forget about what's happening down near the pile tips. And we also see the prediction way over here, almost off scale, of the beta method that was proposed by Meyerhoff. In this case, beta overpredicts F max considerably, while the analytical method provides a greatly improved estimate in this overconsolidated clay. Now, that was a long worm. Remember, we're looking into Roy Olson's can of worms here. I want to extract a shorter worm. The design value of unit side resistance, F ultimate, may not always be equal to F max, which we would predict by one of these models, or predict from load tests on short piles, because of strain softening perhaps and progressive failure as a compressible pile is loaded. There may also be a more subtle reason why F ultimate is not always equal to F max all along the pile, and it has to do with the installation process. Here are the results of several compression loading tests on closed toe steel pipe piles, model piles, in uniform medium stiff clay. In this case, the piles were driven to a shallow depth, load tested to plunging failure, driven deeper, load tested to plunging failure, and so forth, all the while measuring the skin friction, in bearing, and such. Whatever the depth of penetration, F max in the upper 30% of the pile here was always less than it was in the bottom 70% of the pile, regardless of the depth of penetration. This effect could be due to extreme destructuring of the soil at the interface due to large accumulated strains, to reduced effective stresses at the interface from the effects of lateral expansion of the pile upon the passage of the axial stress wave down the pile, or to lateral motion of the pile due to flexural waves that are produced by off-center strikes of the hammer, or perhaps to a combination of these factors. These data suggest that R sub S, the shaft capacity, is about 15% less than one would obtain by integrating F max over the perimeter of the pile. If we assume, this is not quite a correct assumption, I don't want to get into it, but if we assume that failure only progresses down from the head of the pile, and assume, because the pile, of course, is flexible, and assume deflection softening behavior of the relations relating F to pile displacement, relations that peak and then go back down to a residual value, we can actually consider this consideration, or consider this effect of a progressive failure. We can do this by an explicit analysis of the pile and the soil using the well-known TZ analysis, a procedure that was proposed many years ago by Coyle and Rees. A simpler but less general way to determine the effect of progressive failure is to use the Pi3 method developed by Don Murph. Almost everybody I'm talking about is in the audience, and they could lecture better on this than I could, but this method considers the relative stiffness of the pile and the soil, the failure definition, or the failure deformation, W star, and a degradation parameter, psi, which are all defined here in this slide. Piles that are rigid relative to the soil have large values of Pi3 inverse and exhibit average values of F ultimate in the range of 90 to 100% of the average values of F max. But when the pile is flexible relative to the soil, we have small values of pi 3 inverse, and the ratio of F ultimate to F max becomes very sensitive to the degradation parameter psi. So that's something that we need to try to establish. And to apply the method to practical problems, my opinion is that one might estimate psi by conducting consolidated undrained direct simple shear tests to large strains on representative samples of remolded soil. So we understand everything that there is to know in order to design piles for the ultimate skin friction at failure, considering progressive failure and so forth in saturated clay. Well, for those of you who are students, we're going to find out that nothing in geotechnical engineering is ever that simple. And I thank Dwayne Bogard for sharing this case with me, but I want to consider a case of a series of uplift load tests that were reported by Bogard and his colleagues a couple of years ago at the OTC on a pile at West Delta Block 58A offshore from the Mississippi River. Delta. The pile was 0.76 meters in diameter, about 70 meters long, and the soil was normally consolidated or perhaps slightly under-consolidated. It was a plastic clay. The pile was tested to failure at intervals over about 2.5 years. And plotted here are measured relationships between K sub C and depth for each test. Right after driving, or very shortly after driving, a little while after that, a few months after that, and about 30 months or so after driving. You can see that K sub C is decreasing. Well, one might guess that the soil is highly compressible and that at each loading produces pore pressures that have to dissipate, which causes additional consolidation and may be associated arching around the pile, which continually reduces the effective stress at the interface and consequently continually reduces side resistance as we essentially load, unload, and so forth, or some other equally irrelevant explanation. Now, you've probably noticed, if you're still awake, contrary to this explanation, what seems to be happening is quite the reverse. The skin friction is increasing. This is what we had right after driving, and this is what occurred about 30 months later. The skin friction on the average is at least as high or perhaps higher than it was initially, despite the fact that the effective stresses are reducing. So much for the theory of effective stress. So we'll supersede Terzaghi. Or else so much for being able to make reliable measurements of effective stresses against a pile. Now, I don't think this happened because I regard the team that developed the instruments and made the measurements as the best in the world at their business. So what's going on? Well, fortunately, the pile was extracted and examined after the third test, again about 30 months after driving the pile. As in most cases of this kind, a thick layer of clay was attached to the side of the pile. It was something like 75 millimeters, 3 inches thick, and it was hard, basically. When the attached soil was dissected, evidence was found of several shear surfaces at varying distance from the face of the pile. These apparently represented the shearing surfaces that were produced by the successive loadings, which tended to migrate away from the face of the pile. The soil near the surface of the pile appeared to become denser or to harden with time considerably, forcing that failure surface farther and farther away from the pile. Indeed, if this happened, the effective stress measurements, in my opinion, at the interface became irrelevant because failure was occurring somewhere else along a radially expanding shear surface, which produced higher and higher overall resistances. Again, I thank Dwayne Bogard for this photograph, but this is what one of the cross-sections looked like in an X-ray. We're viewing a cut section of soil surrounding the pile in a direction parallel to the pile wall. We're looking parallel to the pile wall. The soil near the microfractures, or shear surfaces, had higher moisture contents than the masses of soil in between them, and the lighter colored soil up here near the interface was considerably denser than the darker soil. This is just like looking at an X-ray of a bone. The bone is light, the flesh is dark. So the lighter colored material is denser than the darker material. The increased density quite possibly was caused by the precipitation of iron, and where that iron came from, if it did in fact come from the environment, is a mystery. but perhaps it was removed from the steel pile and deposited in the adjacent soil through galvanic action. The iron may have become a cementing agent, forcing the outward migration of the failure surface. If this happened, it's probably good news only if we knew how to predict it. So is this a solution to the mystery? Not really, because I'm also aware of another series of pile tests conducted over a period of time in sandy silt, in which K sub C kept increasing with time and F max kept decreasing. Exactly the opposite phenomenon of what we see here. Now, those data aren't available to us right now, so I'll simply say, go figure. Well, it would be nice if we could model in detail every pile that we install in a clay profile or a sand profile for that matter. I might use VCONS because it's a program we developed. Others might use the MIT E3 model, or some people might even use the GESM or some other model. There are many. But such modeling is only justified on projects near the outposts of our experience. For most projects, we have to drop back and use something more tractable, considering the resources we have at our disposal. This often means reverting to a correlative solution, such as the alpha method. The API database for side resistance of piles and clay, developed by Professor Olson and his colleagues in the early 1980s and added to later by others, has been cataloged intelligently and includes correlations between undrained shear strength and F max, the so-called alpha factor, for cases where conditions were relatively well known. Alpha is used rather than beta or some other effective stress correlation because many times the position of the water table wasn't known, and the undrained shear strength was the only measure of soil strength that was available. Not that this is the right way to do things necessarily, but it's the real world in 1999. Simple and Rigdon in 1984, if we look at this pink-colored curve here, which is the one they originally developed, proposed that alpha be related to the ratio of undrained shear strength S sub U to the vertical effective stress, which is, of course, an indirect measure of the overconsolidation ratio. Our observations and analytical models show us that F max over S sub U generally decreases in some circuitous fashion as OCR increases, so this is at least a rational assumption to get us closer to the right answer. However, the method doesn't take into account the differences in the effects of stress reversals, nonlinear stress-strain behavior, including unloading stiffnesses, which perhaps might be different from loading stiffnesses. That might occur in silty soils more predominantly than in plastic clays, degree of anisotropy, and other factors that might be just as important as OCR. Randolph and Murphy the next year proposed the blue curve, and that curve is the current method for design recommended by the API, unless it's been changed recently. It was current as about a year and a half ago. They used about the same data from the database that were used by Simple and Rigdon. A number of years later, in 1976, Kolk and Vandervelde analyzed some of the more recent loading test data and added them to the database, arriving at a curve that's very different from the previous two. That's the red curve that we see here. This curve demonstrates how sensitive our design inferences are to the precise database that we use to develop those inferences, and that's something that you students should keep in mind. The investigators in this particular project added two tests at a normally consolidated soil site called Pintry in the UK. The alpha factor exhibited by the NGI test pile down here was very, very low. And even though the soil was normally consolidated, in the nearby LDP test pile, a separate test pile performed for the large diameter pile test project, had a much higher alpha factor. Kolk and Vandervelde gave this a low weight when constructing the design curve because the pile had been driven in two distinct phases. It was driven about halfway, stopped, and then driven to full penetration. Perhaps this affected alpha, perhaps it didn't. But there was considerable pore pressure dissipation between stages. This might be another one of those cases that could be added to our unsolved mysteries list. These correlative methods apply to relatively short piles, length to diameter ratios of about 50 or less. Each recognizes that lengthening the pile reduces F max to F ultimate. How this reduction is made varies from method to method, as much as a 30% reduction is proposed for very long piles by Simple and Rigdon. I also point out that the method that's used to determine the undrained shear strength is not arbitrary, at least in my opinion. Perhaps Professor Olson can discuss this. But in interpreting his database, Olson defines S sub U according to the following hierarchy of test methods. These are all simple shear strength tests that were available, but UU triaxial compression tests, if they were available, and they were from many sites, were used. If not, unconfined compression tests were used to develop expressions for S sub U and so forth. And this suggests that success in design is related to using tests for estimating S sub U that are equivalent to the tests that were used in developing the database, and I might add as high up the ladder here as possible. Let's change our focus and look at drill shafts for a minute, and particularly drill shafts in cohesive soils. Many engineers view a drill shaft as a non-displacement pile. I prefer to look at it as an entirely different animal. After all, construction involves excavating a borehole with perhaps relatively less soil disturbance than with a driven pile, filling the borehole with fluid concrete, letting the concrete harden, and then loading the resulting deep foundation. Looked at from the perspective of the soil, this is a very different situation that occurs with driven piles, even non-displacement piles. Researchers have not pursued this problem, at least to my knowledge, with the rigor that we pursued the problem of driven displacement piles with the GESM and the MIT models and so forth. So this is a good PhD topic for someone. But at least for now, we're left with the correlative methods for design, most of which are based on the familiar alpha concept. The extent to which drilling a borehole in over-consolidated clay affects the shear wave velocity as one moves away from the wall is demonstrated in this graph obtained using SASW techniques by Kolinsky and Stokey at the University of Houston Experimentation Facility. We can see that for a drill shaft, the effect of stress relief is quite pronounced. It, in fact, occurs to a distance of 2 to 3 borehole radii away from the face of the borehole. And by the way, this scale is incorrect. This is distance from the center of the borehole rather than from the borehole wall. But we can see that one of these squares is a radius, and we go about 2.5 radii away before the shear wave velocity gets back to the free field velocity. At the eventual concrete soil interface, the wave velocities are only about 70% of what they were in the free field. And if we make the reasonable assumption, which is backed up by laboratory tests, that the shear wave velocity is roughly proportional to the square root of the undrained shear strength of the soil, we conclude that the undrained shear strength of the soil has been reduced to about half of its in situ value at the borehole wall by the drilling and stress relief processes. Considering other things that can influence the shear strength of the soil when a drill shaft is installed, Lyman Reese pointed out at his 1976 Terzaghi lecture that once concrete has been placed, water can migrate from the concrete into the soil. This effect is likely to be more pronounced when water-cement ratios are much higher than necessary for hydration of the cement and when the soil has a high level of suction, that is to say when it's dry. In a clay, this effect produces an additional decrease in shear strength, and it may produce swelling. These data are from samples cast against the face of a drill shaft in stiff Beaumont clay in situ. This is not a lab test, but an in situ test. And it demonstrates clearly the effect, where you have a higher water content immediately adjacent to the face of the concrete wall. Water-cement ratio, by the way, in this particular case that was used to maintain concrete fluidity was 0.60, and we would hope that you would not use such high water-cement ratios now. In order to reduce that effect, we ought to be using water reducers to reduce water-cement ratios to the range of perhaps 0.4 to 0.45. But that's a materials problem. So, without an analytical method to predict all of these effects and others that I've just talked about, we return to the alpha correlation to help us with static design. And here's one that I proposed for the second edition of the Federal Highway Administration Drill Shaft Manual, which has just hit the streets. It's based on a simple analysis of parts of 2 databases. I say parts of 2 databases because I've tossed out all the tested sites where the average indicated undrained shear strength is less than about half an atmosphere, since drill shafts for bridge foundations are not often used in such soils. The well-known alpha correlation of Kolhawy and his colleagues for drill shafts is somewhat different from this one, particularly at the low end of the shear strength axis, because some such tests are included in his database. And he concludes that the alpha factor for very low shear strength is higher than I've shown here. In any event, this correlation assumes that one uses the results of UU triaxial compression test to determine S sub U. Beyond S sub U of about 2.5 atmospheres, we treat the geomaterial as intermediate or something between a hard soil and a soft rock, where we might use something different than this to evaluate alpha. Alpha is about as uncertain here as in driven piles for both similar and different reasons. And the uncertainty, which I'm sure Dr. Duncan is going to talk about, is something that we should always keep in mind as geotechnical engineers. The similar reasons are associated with characterization of shear strength profiles. In drill shafts, alpha is affected by the time the borehole is open, the roughness of the borehole, the fluid pressures in the concrete, the amount of excess water in the concrete, and perhaps other factors. These effects are of little concern with driven piles, of course, which is the reason for my stating that drill shafts are different animals. And if Professor Duncan will forgive me, I want to look at a couple of statistics. If we look at the databases from which we drew this last figure, we can make some simple statistical calculations and conclude that this particular alpha method is slightly conservatively biased. On the average, it predicts slightly less capacity than we've measured, but it has a relatively high coefficient of variation, in this case 0.36. Now, for those of you who haven't taken statistics in a year or so, the coefficient of variation is just the standard deviation of the data divided by the mean value. In order to reduce the coefficient of variation, and of course that affects what kind of factor of safety we use and what kind of resistance factor we use if we're working in an LRFD context. I won't get into that, but it's something that's very intriguing. In order to reduce the coefficient of variation, which we'd like to do, and increase our reliability of our side resistance estimates, we might go back and interpret our load test database according to the beta method, because it's an effective stress method, and we all know that effective stresses are better than total stresses, right? Well, Meyerhoff suggested this method that I won't read here, but it's similar to the beta method for piles, slightly different. In his 1975 Terzaghi lecture, and more recently Kolhawy and his colleagues have developed an improved version. However, if we look at the database of Chen and Kolhawy, we conclude virtually the same thing that we concluded about the alpha method. It's biased slightly conservatively and has a coefficient of variation between 0.35 and 0.4. Again, the uncertainty seems to lie largely in the effect of construction, so that at the present there's really no compelling reason to use the beta method in preference to the alpha method when designing drill shafts in stiff soils over consolidated clays, even though it might appear to or appeal to our good sense of soil mechanics. Now, drill shafts offer obvious advantages when we have to put the foundation into rock. I'll conclude my little foray into drill shafts and cohesive geomaterials by discussing this subject very briefly, at least regarding soft rock, which I arbitrarily define as rock with a compressive strength of about half of that of ordinary concrete. Two factors have long been understood intuitively to affect side resistance in such foundations: the roughness of the cut of the borehole and the presence of smeared or degraded material at the interface between the concrete and the rock. Soil-like smeared material is produced by drilling in many argillaceous or clay-like soft rocks when free water is present in the borehole. Khalid Hassan, one of my former graduate students, is one of a number of investigators who looked into one or both of these issues in some detail. Since I'm familiar with his work, I'll make some comments based on his studies, which were performed in the field and also by using finite element modeling of soft rock with frictional, drained, and dilational interfaces. And I'll describe the materials for simplicity in terms of their unconfined compression strengths. The sinusoidal geometry that you can see here of the discontinuous interface is shown on this slide. It's basically working with a wavelength of 1 foot and an asperity height of 1 inch, with the possibility of a smear zone being a ½ inch thick. That's a very brief discussion of what he did. If we analyze the interaction between an axially loaded drill shaft and that kind of soft rock using a reasonable constitutive model for the rock, you come up with a typical set of shear stress contours around the rock asperities that look like this. The red zones represent gouge zones in the soft rock. This is the rock, this is the concrete. What seems to be happening is that we're getting something like a side bearing failure under these rock asperities, where there's a circular or rotational failure around the asperities. We're developing much higher than the undrained shear strength here because there's some drainage in the rock which consolidates very quickly, but very little shearing resistance here near the bases of the rock asperities. On the whole, on the average, we end up, for fortuitous reasons, with an average side shearing resistance that's something in the order of 1/2 of the undrained shear strength of the rock, or undrained compression strength of the rock, I should say, the unconfined strength. The complete modeling sequence produces the relation of average shear stress F to settlement shown here. I think this is fairly interesting. The red line represents a socket that's 6 meters long and about 0.6 meters in diameter in the rock that's described on this slide, which I won't take the time to get into. If we remove the roughness pattern and assume that we have a smooth frictional interface, we get the second curve from the left, this dashed line. We can see that this roughness pattern actually triples at a settlement of 25 millimeters, or roughly 1 inch. It essentially triples the skin friction. So roughness in soft rock is extremely important. I'll not talk about this curve here, but I'll talk about this curve here. If we have a rough interface and we put smear, a soil-like material that has only 20% of the shear strength of the rock in the zone in between the concrete and the soil, or concrete and the rock, even though the asperities are much thicker than the thickness of the smeared material, we get a load settlement curve that looks like this, in which we get virtually no effect from the roughness. So getting the sides of the borehole are extremely important. And I'll make a very strong statement here that some of the drilling practices that we use in Texas are rather bad. We allow our contractors to dump water in the hole to help make the soil or the rock sticky so they can get it out easy. This is just contributing to this problem. We don't force contractors to case off surface seeps and so forth, which we should do. We need to keep the rock as free from these kinds of things as possible. Let me relate a short case history just to show you give you some feel for roughness. This is a case history in which soft rock with very low RQD was encountered. It was time to punt. The RQD values were from about 0 to 30%, but we did have, on the average, about 75% to 80% recovery. The mean unconfined strength of the harder sections of the rock that could be recovered and tested was about 3.6 megapascals. The rock was a series of vertically stacked lava flows that over time had weathered extremely differentially, such that the coefficient of variation of the compressive strengths of the rock cores that were recovered, this doesn't include seams and so forth, was still about 0.6, a horribly variable material. The design value for unconfined strength of the attacked rock was selected such that we would have 80% confidence that the actual value of shear strength for the attacked rock would be higher than the design value. This allows us to use in an ASD process factors of safety that were equivalent to those that would be used for more uniform sites. If only we could assess the effect of what we didn't have a clue about, the materials in the seams between the intact rock. So we installed a test shaft in a 1.2 meter diameter borehole. It was artificially roughened and calipered. As you can see here, the red line representing the actual measured roughness of the borehole. It wasn't a series of very nice shear keys, but it was rough, and it approximated very, very crudely the roughness pattern that we were able to model in the computer, which was sinusoidal. Not bad in terms of asperity amplitudes, but not great in terms of shapes. And this is a picture looking down that particular test shaft with the sunlight. And that's a rough shaft. That's what that shaft looked like. If you're an inspector and you look down a drill shaft and it looks like that, that's rough. It's not gun barrel smooth, for heaven's sakes. Well, in modeling the load test. We performed the load test using an Osterberg cell, and the results of the test, shown with movement positive here, downwards, like it was a compression test, are all compared with several analyses using the sinusoidal interface surface. This line here is the load test, and these are all modeled relationships. And to make a long story short, using an appropriate value of Young's modulus for the intact rock, we concluded that we had to, in our mass model, reduce the strength of the intact rock to 40% of Q sub U to produce behavior that was reasonably similar to that measured. And we did a pretty good job, except that the initial slope of the load movement curve was too soft, and part of the stiffness mismatch was because the sinusoidal model only considers long wavelength effects, whereas we know that some shorter wavelength disparities existed in our borehole profile. These tend to stiffen the initial load movement response because they shear off at small deflections. So with this approach, we were justified in using R is equal to 0.4 for this terribly heterogeneous rock for design where we had a low RQD. This was the only way that we could back into some reasonable effect of the seams. I've often asked if a load test can be run to measure side resistance for a large diameter drill shaft using a small diameter socket. It's a very practical problem. If we can, it's very cheap to make these measurements. And the answer is probably yes if you don't count on interface dilation to provide part of the side resistance. The asperities shoving the rock aside, creating excessive or higher effective stresses and increasing the shearing resistance. But that can be wasteful. If we use design values for side resistance that are associated with a naturally or artificially roughened interface, we need to consider the effect of diameter, as illustrated in simplistic terms in this figure here. Loading thrusts the rock radially outwards and increases the normal effective stress along the interface. If we assume the rock to be elastic, which of course is an oversimplification, the radial stress is proportional to the heights of the asperities and inversely proportional to the radius of the socket, provided the asperities don't shear off. That's another oversimplification, of course. But given that assumption, or given that set of assumptions for a given roughness pattern, the smaller the diameter of the socket, the higher the value of normal interface stress and the higher the value of F max for a given pattern, for a given asperity height, and for a given wavelength. The effect is illustrated here using results from a computer program called Rocket that was developed by my colleagues in Australia. A 2 meter diameter socket with a moderately rough interface and soft rock develops a maximum side resistance right here, only about 42% of the maximum side resistance that's developed in roughly a 1 foot diameter socket. So use of results from a test on a small socket to design the large socket without consideration of this scale effect would be unwise, especially if we don't have any smear material, which is what we have here. I might add that work that we've done experimentally tends to back up this model, at least in terms of the direction of movement. The larger the diameter, the smaller the shearing resistance. So here we come to practical considerations. I believe that Hassan's model and Rocket are both practical ways of simulating sockets in soft rock with due considerations of seams and joints, as we've discussed. However, the method of Kolhawi and Poon, which has been derived from a database of socket tests in both clay and rock, might be a little bit easier to work with, at least for design purposes, and that's that method there. It gives us values of F max normalized by atmospheric pressure, P sub A, for sockets of varying estimated roughness. Notably, the ratio of F max to unconfined strength jumps considerably as we transition from clay to rock, right here. And that's been the source of a lot of controversy. Test shaft diameter and sampling effects may very well contribute to this, because the test over here for fairly large diameter shafts, the test over here for fairly small diameter, and they have not considered the diameter effect in their equation. However, the little relation given in the upper right-hand side of the slide, which considers a roughness factor, provides a good preliminary design formula for drill shaft sockets in soft rock. Would I use this method or the others that I've talked about, Rocket, Hassan's model, and so forth for final design? Probably not for an important structure unless I verified the method through load test, which gets us back to Terzaghyi's admonition. The issue is whether or not the value of the external skin friction in a pile, the value of external Fmax, can be taken for design purposes to be equal in compression and uplift when we have a sand, a siliceous sand. We won't get into the issue of calcareous sands. U.S. engineers have long held that there's no difference and have written the API guidelines so that this point of view is reflected. Others cite evidence to the contrary. For example, when the pile is loaded in uplift, there's a Poisson's effect in which the pile will likely contract a little bit, which would reduce the radial effective stress at the interface. And since the pile stretches, there's also a net reduction in the vertical effective stress in the soil surrounding the pile at any depth, which also reduces its shear strength. The vertical effective stress increases in the soil near the pile at a given level due to load transfer from higher elevations when a flexible pile is loaded in compression. These are measurements of that effect that were made in a large pressure chamber, and conversely they decrease when the pile is loaded in uplift. These are typical readings. Now, the change in vertical effective stress adjacent to the pile is essentially proportional to the value of the average side load transfer above the level of interest, termed here F sub A, and the effect isn't enormous. We're talking about maybe less than 10% changes in vertical effective stress, 10% of the average side resistance above the point. However, the increase or decrease in vertical effective stress is clearly observable, and therefore, in consideration of this fact, we should take a look at the TZ curves that we might measure in the piles in which we measure these stresses, and we can see, in fact, in 12 tests, looking at 4 different levels here, it's very clear that we're getting higher skin friction, around 1.04 ratio to the horizontal effective stress in compression compared to about 0.77 in uplift. That is to say that the skin friction in uplift is about 75% of what it is in compression. There's no doubt about it. It's a very clear phenomenon, and yet people do not believe it. I'll leave it at that. Some people in the audience don't believe it. But we can discuss that at Jean-Louis' house and break some vases and glasses and things like that. Let me conclude by saying that engineering managers may view some of the methods that we've talked about as being too complex, too expensive. After all, we might have to have pressure meter data to get our moduli. We might have to have, and K-naught factors, we might have to have CPT data. We certainly need to have a handle on the shear modulus variation in the soil, and we need to make some estimates, perhaps, of the roughness of the pile surface, either a drill shaft or perhaps a driven pile, to make accurate calculations of what the shearing resistance is going to be on the interface. And we also have to recognize that Fmax varies with position along the pile, direction of loading, and perhaps with the toe condition, which I haven't discussed. I'll also submit that Fmax depends upon the method of installation. So just use N over 50 and get on with being productive. We don't want to do all these calculations. Use of methods like these, which I think reflect reality better than some of the old methods we're all locked into, requires more time and effort by knowledgeable engineers. Higher engineering cost, if you will, that in the end will lead to greater economy and greater safety in the constructed foundation. I'm alarmed, as I'm sure many of you are, to see a growing complacency among owners regarding the technical efforts that need to go into foundation engineering. That foundation design is a solved problem, a done deal, that can be relegated to the C students or even related professionals who have very little appreciation for the complexities of the problem and the consequences of wrong decisions. We all need to do a better job of selling our real engineering capabilities to owners and other decision makers in terms that the marketplace can understand, and return to the practices that made us a valuable resource to society. I'd finally like to conclude just by thanking the individuals whose names you see here. Many of them willingly served as sounding boards for my thoughts, some of which were less than solid and ended up in the trash basket, thanks to them, and for providing me with technical information, some of which I used and most of which I didn't have time to use. I'm especially indebted to my colleagues and former students at the University of Houston, whose names appear in white. and whose data and computations I have shamelessly used in this presentation.